Jules Verne thrilled the world with tales of fantastic journeys to the bottom of the ocean, the North and South Poles, and the Moon. Back in the 19th century, none of his adventures was thought possible. Since then, we've realized them all, except one. Is science and technology finally ready to fulfill Verne's ultimate dream? Can we journey to the center of the Earth? Amiens, a small town near Paris, France, was home to one of the most visionary authors of all time. He's known as the father of science fiction. Some say he invented the future. He was Jules Verne. 150 years ago, he wrote tales of adventure and science fantasy, much of which has become science fact. His heroes flew to the moon 100 years before the first real attempt and circumnavigated the globe in days at a time when it took months. Like all Verne's bestsellers, Journey to the Center of the Earth was a product of rich imagination and research. How much did his scientific crystal ball get right? When Verne was writing Journey, little was known about the interior of our planet. The Earth sciences were in their infancy. But the 19th century was a time of great discovery. Journey is set in 1864. Verne's heroes are German professor Otto Lidenbrock, his nephew Axel, and their Icelandic guide Hans. Their quest takes them to the center of the Earth and back through time. Verne's prehistoric monsters were the real thing. The underground ocean he invented. Science and technology, thrills and spills, no other writer captures so well the excitement of exploration and discovery. How much did he get right? Since Verne's time, we've conquered space. But if we are ever to journey to the center of the Earth, we still have a long way to go. Who hasn't, as a child, daydreamed about digging through the Earth and popping up on the other side of the world? If we could do this, where would we end up? Jumping into a hole in Spain would bring you out in New Zealand. Argentina would link to China. And from Miami, you could drop in on Perth, Australia. If these dream tunnels were real, you could just jump in and let gravity take over. Gravity would cause you to accelerate towards the center and then slow you down again, allowing you to step out on the other side. 8,000 miles later. If we could dig a hole like this, what would we find? At the Earth's center is a massive ball of iron known as the core. An outer core of molten iron swirls around it. Next is the mantle, slow-moving hot rock, 1,800 miles thick. In contrast, the crust, the part we live on, is thin. In fact, it's broken into pieces called plates. The crust plates are always on the move. A journey down an eroded canyon is like a journey back in time, because it shows how the Earth's crust has changed and continues to change. Layer upon layer of rock has built up on the surface of the Earth over millions of years and is relentlessly worn away by wind and water. But the deepest canyon on Earth is only 2 miles deep. It's 4,000 miles to the center of the Earth. But how far is that? This airplane is flying at 12,000 feet. The parachutists will fall 7,000 feet before opening their chutes. They free fall at over 100 miles an hour. At this speed, they'd reach the Earth in just over a minute. If they could continue like this to the center of the Earth, it would take over 36 hours. It's as far as Chicago to London. Caves were an obvious starting point for a journey to the center of the Earth. The deepest cave Verne knew of was at Huachara, Colombia. It had been explored to 2,500 feet. Not one for half measures, Verne wondered what would happen if his explorers went much deeper. Jules Verne reveled in technological invention and outfitted his heroes with electric lights powered by chemicals. He knew naked flames were a hazard underground and came up with this original solution at a time when gaslight was still a luxury and electricity known only to scientists. The geologists of the day thought that erupting volcanoes must leave giant tunnels underground. Verne was fascinated by geology and led his explorers past rich seams of minerals and precious metals, and into cathedrals of stalactites and stalagmites built of lime by a billion water drops. Caves had been tourist attractions since the beginning of the 1800s. Verne used these as a route to the Earth's center. But not caves like this. Modern caving began in the 1880s, directly inspired by Journey. Pioneering cavers didn't have the high-tech gear we take for granted. Wetsuits were unknown. Instead of lightweight alloys, their tools were made of steel by blacksmiths. They made their own ropes from hemp or silk, not waterproof man-made fibers, and had to hire porters to carry all the heavy equipment. Today, caving is more popular than ever. Even so, it's thought 9 out of every 10 caves are yet to be discovered. These are the new frontiers in the exploration of our planet. But these days, we know we can't get to the center of the Earth this way. The deepest caves go down only 5,000 feet. But need, and some would say greed, have driven us to penetrate much further into our planet. Early mining started as simple holes in the ground, but as the surface deposits have been used up, we've had to go deeper, digging shafts and tunnels. And if the prize is big enough, it's worth going a long way down. These men are plummeting towards the center of the Earth. They are in search of gold, a metal valuable enough to dig 2 miles down to get it out. The mine is so deep that the cable would break under its own weight if it was continuous. That's why the miners have to change cages halfway. They're already 2,000 feet below the bottom of the deepest mines Verne knew about. Today, this is the deepest mine on Earth. It's also the deepest anyone has been into the Earth's crust, and these miners do it every day, going to work. They're 12,000 feet down. There's a way of going still deeper that doesn't involve digging, but it does require diving. The deepest place on Earth is at the bottom of the ocean. In 1960, a submersible called Trieste got there. A century behind Nautilus, the submarine in Verne's book 20,000 Leagues Under the Sea. Apart from Nautilus crew, the two men aboard the Trieste are the only people to penetrate this far into the abyss. More men have walked on the moon. Here, the ocean is deeper than our highest mountains. The Trieste dived as far from its surface as the airliners cruising overhead, 7.5 miles. We can get deeper than that by drilling. This is the site of the bid to drill the deepest hole on Earth. In Verne's day, drilling for water was routine, down to around 100 feet. But 5 years before Journey, drills were used to find oil. The technology went into overdrive, but even a century later, the Russian goal of 40,000 feet looked like a step too far. A German attempt had failed at 30,000 feet because the rock was so hot and soft, it sealed the hole. After 14 years, the Russians made it. Core samples were eagerly analyzed by geologists. No one had ever seen rocks from this far down. So how near have we got to the center of the Earth? Cavers venture 5,000 feet down, while miners work at 12,000 feet. And the Trieste plunged to 34,000. Up to now, we've drilled to 40,000. But it's 21 million feet to the center of the Earth. We've barely scratched the surface. Why does this man keep scrambling and squeezing his way down? He's in search of something more precious than gold. Jules Verne lived at a boom time for science, when the natural world took center stage. He trained as a lawyer, not a scientist, but started to devour scientific papers as a student and kept up with new discoveries all his life. Always hungry for material, Verne picked the brains of many top scientists. Charles St. Clair Davy, a world expert on volcanoes, provided inspiration for Journey. In the middle of the 19th century, the big questions about the Earth were still to be answered. How old was it? How was it made? For many people, the answers were a matter of faith. The problem was, science was suggesting that may not be true. Darwin had just published his theory of evolution. The world and all living things weren't made in 6,000 years, but millions. Knowing about fossils had prepared Verne for that, but fossils embarrassed the faithful. How could their God let his creations go extinct? When mammoth fossils were found in America, even Thomas Jefferson believed they must still be alive there. It was just too good an opportunity for Verne to miss. In his novel, Verne conjured up a scene in which the professor, Axel, and Hans would find more than old bones. What if they found, hundreds of miles below the surface, ancient species living on? We're still finding fossils all over the world. We have better tools than the hammers and chisels Verne would have recognized, but freeing the precious bones from the rock is still a painstaking task, requiring skill and patience.
Fossils are the remains of plants and animals that once lived. So, for example, if you have a creature that lives in the sea, when it dies, its carcass would fall to the bottom. And over time, the bones would be picked clear of flesh by any scavengers down there. And then it would eventually be buried, presumably by sand or silt. And then in the course of maybe tens or hundreds of years, with pressure of more sediment on top, the bone is infiltrated with minerals. And there you have a fossil.
In Verne's day, enthusiasm often got the better of expertise. Bones of different species might be assembled to make animals that never walked the earth. Things are very different today.
So the paleontologist is a detective who looks at these bits and pieces of ancient plants and animals, puts them together using anatomical knowledge, comparisons with modern forms, and you can literally bring the past back to life.
This may be the oldest plant-eating dinosaur yet found. It lived on tropical islands like those in the Caribbean. So why, Verne would have asked, was this one found in Britain, where it's cold and damp? Because 200 million years ago, Britain was way down south, near where North Africa is today. And the sea level was so much higher, the hills of Britain were islands.
By Jules Verne's time, people understood a little bit about the history of the Earth. Geologists had been studying the sequence of rocks for about 30 years or so. And they realized as you go back in time, you got into more and more ancient rocks, and as you looked at the fossils, you got more and more unusual and ancient-looking creatures.
In his book, Verne was able to bring the past back to life and adapt species of the present to life underground. He knew that plants couldn't survive there since they need sunlight, but figured that fungi could thrive. In the higher temperature and humidity deep down, he had his heroes encounter mushrooms of awesome proportions. But what can really be found on a journey to the center of the Earth? Bats may be the best-known cave dwellers, but they only use caves as hotels, going out at night to feed. You have to go deeper to find stranger life. Apart from the oceans, no other habitat is so alien to our experience. Most of the animals that live here came from the surface, perhaps fleeing changes in landscape or climate. Over thousands of years, they've adapted to this dark world. They need no coloration to protect them from the sun, and no eyes to see, since they live in total darkness, finding their food by touch and smell. Cave-dwelling animals, known as troglodytes, are difficult to study. They live in such tiny crevices they may never be found, even by the most intrepid explorers. But it's other creatures down here that are exciting scientists today. Creatures so small you can't see them with the naked eye. And to work with these elusive life forms, John Parks faces a commute that most people would do anything to avoid.
We do find life in the Earth, despite the fact that the deeper you go, the higher the pressures and the higher the temperature. But life is very small, it's microscopic organisms, mainly bacteria. And these organisms can survive those conditions. In fact, some can grow at temperatures as high as 113 degrees centigrade, much higher temperatures than boiling water. The startling thing about life in the subsurface is that the first estimates of the total bacterial population there indicate that they represent about 70% of all bacteria on Earth. So the majority of bacteria actually reside in the subsurface. They're not in this thin veneer very close to plants and animals we're used to.
But what do bacteria find to eat down there? New discoveries suggest it may be the Earth itself. In Verne's day, science believed that all caves were created by water, wearing away the rock. But is this right? These caves were formed millions of years ago, before the sea level rose. Now they're only open to intrepid diver scientists like Sam Smith. She believes it's not water that eats away the rock, it's bacteria.
I think that without bacteria, caves and limestones would not exist. You really do need the bacteria to form carbonic acid or other acids in the soil zone above where the caves might start to form or develop, which then starts to carve out the cave. There's no doubt that over time water corrosion also plays a role, but bacteria need to be there as well.
Microbes or meteors? Join our teams of scientists as we go deeper still, searching for clues about what formed the Earth. Sam's study site is in the Yucatan Peninsula in Mexico. The caves extend for 50 miles and are up to 400 feet deep. If Sam is right, rock-eating bacteria hollowed them out, and they're still at it. The quest for the bacteria takes her deep into the underwater maze. This is a dangerous place. Sam's exploration is at the limit of diving technology. There are only 3 scientists in the world experienced enough to dive into caves this deep. All their equipment has a backup, or even 2, since problems must be solved on the spot. This is no place to get lost with your air running out. When Sam finally gets to a spot where the rock-eating bacteria could be at work, she makes sure the samples she collects will be perfect.
To take our samples, we use 10-meter length tubing, silicone tubing, that basically allows us to take a sample at a point 10 meters upstream of us, and it minimizes the diver's disturbance to the water, so that sample is as sterile and as clean as possible.
Having come this far, it's vital that Sam doesn't contaminate the samples with her own bacteria. Only then can the return journey begin.
After we've collected the samples, we immediately take them back to the cave surface, where they are put on ice right away and kept on ice until we get them back to the field lab.
The bugs are cooled to 40 degrees and flown in this standby state from Mexico to Sam's lab in England. It takes about 8 hours. A Jules Verne hero managed to race around the world in 80 days. It was 10 years after Verne wrote Journey that Louis Pasteur put bacteria on the map. And for another century, the world would see bacteria as a nuisance. Now, scientists like Sam suspect they may become a vital and inexhaustible commodity. First, she wants to know how many rock-eating bacteria there are. She wants to know if they're all the same type. Most of all, she wants to verify that the acids they produce can carve out caves. If Sam's right about these microscopic miners, it's a giant step forward for geology.
It's something that's quite exciting to think that something so small, so the bacteria, which are about a micron in size, so 1/1,000,000th of a meter, can actually alter something so large and have such a large impact on the environment around them. Bacteria exist everywhere, in the air, in water, land, sea. And anywhere we've looked for them, so far we've been successful at finding them.
So, will we find bacteria at the center of the Earth?
If you want to think about how deep we could go and still find bacteria, it probably is temperature dependent, but we haven't reached that maximum yet. We haven't looked deep enough yet where they haven't been there.
Because they can eat what we can't eat and thrive in conditions we find extreme, bacteria may turn out to be the Earth's real buried treasure. They're already at work in our homes.
We all are used to using biological detergents in washing powders. These come from organisms that can grow at 60 degrees centigrade. If we can get organisms growing at 130, 150 degrees centigrade, basically they could make superb catalysts for a whole range of different compounds.
Unlike some other resources, there's no shortage of bacteria. This core sample of rock comes from 200 feet below the surface. It contains as many bacteria as there are people on this planet. We've come up with bacteria wherever we've drilled, and however deep. They can survive for millions of years, buried alive, without food or oxygen. Some see them as an infinite, untapped labor force. The first oil wells came online in Verne's time, but the era of easy-to-get-at fossil fuels is almost at an end. Unless these new microbial workers can help us out.
We know that we leave something like 40% of all the oil in reservoirs in the ground. We can't extract it. And for example, if we're able to manipulate these deep organisms, they might be able to convert the oil into gas, and then several years later we could come back and we've got a viable gas field instead of a spent oil field.
Verne's adventurers didn't strike oil, but they did find platinum and gold. They decided these were too deep ever to be mined. Verne meant by men. He hadn't reckoned on microbial miners. The idea of using microbes to extract minerals was beyond even Jules Verne's imagination. But because some types of bacteria digest rock, they're already being used to separate metals from ore. And that's just the beginning. One day, we'll be able to put bacteria to work at depths we just can't tolerate. Until then, we'll go on doing it the hard way. Mining at 12,000 feet is difficult, dangerous, and expensive. Every mile you descend, the Earth gets hotter by 50 degrees. Here, a single bacterium can live for 1,000 years on a diet of nothing but rocks. Bacteria living here are natural alchemists. They play an integral role in creating deposits of gold. As they break down the rock and mineral ores, the bacteria attract molecules of gold to their outer skin. Over millions of years, the gold builds up to form a glittering gold deposit. The mine uses more electricity than a small city, making 80,000 tons of ice a day, and lifting 10 tons of ore 2 miles to extract each and every ounce of gold. It's the rock's history that lets us mine here this deep. Most places would be simply too hot. But in South Africa, the Earth's crust is older than in most other places, so it's had more time to cool. 2.5 billion years ago, the gold accumulated on the surface in a lake. Over time, the land and the gold was tilted and forced down into the Earth. No richer deposit has been discovered. Three-quarters of the world's gold has come from it, but that's only 2,000 tons. To find out why metals like gold and platinum are so rare, we must go back to a time when the whole of the Earth was molten. $4.6 billion years ago, a continual rain of meteorites pounded the molten Earth. Each strike brought with it more rock, making our planet bigger and scattering metals over the surface. Then, a giant asteroid struck. Its massive iron core didn't stop on the surface. It sank towards the center, and it attracted all the Earth's metals to it as it went. The asteroid's lighter, rocky debris went spinning around the Earth. The fragments were drawn together by gravity. Within a year, they formed our moon. That's why the moon has no metal at its core. And it's why metal is rare in the Earth's crust. It arrived much later, in meteorites from outer space. If we want much more metal, we must go to the Earth's core. It's made mostly of iron and nickel, but 1% is gold. That may not sound like much, but the core is so vast that its gold could cover all the land on Earth, knee-deep. In South Africa, the miners are already going deeper in search of more gold. They plan to follow the seam to 3 miles down, where keeping the mine cool could account for 20% of the mine's outlay. They may need temperature-controlled suits or robots to extract the precious metal. The northern and southern lights, beautiful and benign. But what will happen when the lights go out? In 1860, no one really had a clue what went on 4,000 miles below their feet. Many people still believed that the Earth was hollow, a theory put forward 200 years before by the astronomer Halley of comet fame. In 1823, an American, John Cleves Sims, had led an expedition to prove that Halley was right. He didn't succeed. Jules Verne knew of Sims' theory and kept an open mind. But he led his explorers into an immense underground cavern in which they had to cross an ocean lit by lightning and magnetic storms. This was pure fantasy. But the scene also drew on fact. Verne's research had convinced him that traveling down into the Earth would be like going back in time. So the creatures stirring in the deep were real. 200 million years ago. Plesiosaur. The first remains of the long-necked reptile were found in 1820. The dolphin-shaped ichthyosaur, unearthed in 1809. Verne was right. There is an ocean at the center of the Earth. A tempestuous sea of molten iron. As this surges in turmoil around the solid inner core, it generates magnetism. A colossal force field stretches into space, protecting us from solar radiation. Sometimes we can see it. The northern and southern lights put on a show when electrically charged fragments from the sun collide with the magnetic field. But there's evidence that its power is fading, and that could mean we'll be exposed to a lethal dose of cosmic rays. At Harvard, Jeremy Bloxham is trying to find out why this is happening.
One of the goals of our research at the moment is to try to develop a capacity to forecast what's going to happen to the magnetic field in the future. And this is of particular interest at the moment because over the last 150 years we've seen the strength of the field decrease by almost 10%. And that's a rate of decrease which is characteristic of the field heading into a magnetic reversal. So an interesting question is, will the magnetic field actually reverse?
A magnetic reversal, or flip, means the North Pole becoming the South, and vice versa. Compasses will point the wrong way. Navigation will be literally turned upside down. But this won't be the first time it's happened.
There's been maybe 60 reversals in the last 30 or 40 million years. So in geological terms, they're a very frequent event. Just in the timescale of human experience, they're a very rare event.
But what will happen in a flip? Will we be able to find our way around? Today, magnetic compasses are used less for navigation. Instead, we use GPS satellites, which won't be affected. But before the flip, the Earth's magnetic shield will fail. And without it, satellites bombarded by radiation will burn up in space. It's not only human navigation that will go wrong. many animals rely on internal magnetic compasses for migration. But no one knows how they will manage. But flips don't happen overnight. The force field fades slowly. Jeremy Bloxham is watching it closely.
There's a variety of techniques which we can use to see how the field is changing. We have modern measurements from spacecraft which are in orbit specifically to measure the magnetic field. We have permanent magnetic observatories set up at various locations around the world which continuously make measurements of the magnetic field. But measurements like that only tell us what's happening on a timescale of decades to perhaps a century for the longest running observatories. But the magnetic field is changing on much longer timescales, so we need to be able to ask, how can we find out how the field has changed over centuries?
Fortunately, navigators long depended on the magnetic field, and we've learned a lot about its variations from their charts. And the changes continue. Today, magnetic north is leaving Canada and heading across the Arctic Ocean at a steady 10 miles a year. But it's one thing to know the poles are moving, another to know why.
The Earth's core is liquid iron, or mostly liquid iron, and the motions of that electrically conducting iron can create what we call a dynamo. But the details of that process, how it actually works, are still very poorly understood.
To understand it better, Dan Lathrop has built a working model of the Earth's core.
We've been building a sequence of experiments, progressively larger and higher powers, to try to get the same parameters as occur in the Earth's outer core and try to understand how the Earth generates its magnetic field.
Yeah, keep an eye on the temperature too.
We like to know what sets how strong the Earth's magnetic field is. We also would really like to understand what causes all of the changes that are seen, anomalies in the field and reversals, and to be able to both understand what causes them and be able to predict them.
The floor of the Atlantic Ocean bears witness to flips of the past, because lava lines up with the magnetic field as it solidifies. The problem is, flips aren't regular. To predict the next one, we must know what's going on in the core.
Okay, going to spin to 10 RPS.
We have two different types of experiments that we're currently working on. In the first experiment, we actually drive propellers that churn the fluid, propeller on either side, that sets up this sort of wildly turbulent flow.
Okay, getting ready to run at 10 RPS. Ready to go.
At the heart of Dan Lathrop's dynamo is a sphere filled with hot sodium. Electrically, sodium behaves like molten iron, but it's 1,000 degrees cooler. A propeller creates the sort of turbulence thought to be caused by the rotation of the Earth. Up to now, they haven't been able to generate a steady amount of magnetism. But they have learned that small changes in speed and temperature significantly affect the magnetic field.
In the other experiment, we have a geometry very close to the Earth's outer core, where we rapidly rotate a sphere, which has a layer of liquid metal, and then we heat the outer edge and cool the inner sphere and set up convection, sort of like you might have boiling in a pot, making pasta. In this case, it's sort of the churning of the liquid metal that gives rise to a turbulent flow that affects the magnetic field.
The next step is to build a bigger model. After all, the real Earth's core is over 4,000 miles in diameter.
There are really three main questions that we're trying to understand in the experiments. We'd like to know what sets how strong the Earth's magnetic field is. We also would really like to understand and what causes them and be able to predict them. And the last thing is we'd like to know what are the limits to having a dynamo on a planet. So why does the Earth have a dynamo and Venus does not?
Einstein insisted the question of how the Earth generates so much magnetism was the most important unsolved puzzle of physics. No one knows when the next reversal will happen. One thing is certain, though. The magnetic poles will reverse. Scientists in Verne's day knew that magnetism came from within the Earth, but not about magnetic reversals. Yet he predicted a magnetic flip. His explorers had been traveling for months. Professor Lidenbrock reckoned they were almost at the center of the Earth. They stopped to draw breath and take a bearing. That's when they realized something was wrong. Their compass had gone crazy. Had Verne seen into the future again? He certainly knew of the connection between magnetism and electricity because he tells us that the compass flip occurred during the storm at sea, when lightning struck the boat. Don't try this at home. Fortunately, this isn't the only way to find out when the volcano's going to blow. Volcanoes are the richest source of rock from deep inside the Earth. The most active is in Hawaii. This is the closest we can get to what it's like at the center of the Earth. It's a reminder of the heat and power hidden beneath the surface of our planet. Kilauea volcano has been spewing out lava for thousands of years without a let-up. It single-handedly built the island. Molten rock, called magma, surges up from near the Earth's core and blazes through the crust. The stream, known as a plume, lets inner Earth let off steam. It's like a safety valve.
We believe that the volcanism at Hawaii is ultimately caused by a hot plume rising up beneath it, which occurs because material at the bottom of the mantle is heated up by the core. The core's maybe 2,000 degrees C hotter, and heating it up causes it to become less dense, and then it rises through the mantle. A good analogy is with a lava lamp that you might see in someone's living room.
It's lamps like this that show us what's going on in the Earth's mantle, the layer between the core and the crust. Rock, heated by the core, rises while cooler material sinks from the surface. It's this never-ending process, known as convection, that pushes magma to the surface, where it erupts as lava.
Hawaii is a bit of a special example. It's the most active island volcano that there is. It erupts with extreme frequency, and it's also exceptionally runny, and so the lava flows tend to move very fast, and they have a high proportion of these so-called pahoehoe surfaces, which are these beautiful, smooth, ropey textures that you see.
Lava can build, but it can also destroy. It can seldom be diverted, and it wipes out anything and anyone that gets in its way. Early geologists assumed that such torrents of molten rock flowing out of volcanoes must leave huge voids and caverns behind them. Jules Verne's explorers followed one of these lava tubes as they approached the center of the Earth. But the Earth had one last surprise in store for them. As the professor, Axel, and Hans neared the center, their path was blocked by a rock fall. There was no other route, so they decided to blast their way through. Verne knew very well that molten rock trapped deep in the earth is under huge pressure. If that pressure is released, it can start a volcano. That's why blasting was a risk. In classic literary tradition, the eruption they triggered blasted our heroes to the surface without as much as a singed eyelash. Eruptions are how the Earth recycles itself. Convection currents in the mantle carry rock to volcanic vents and fire it back to the surface. Volcanologists today can't get inside an active volcano, but they get up close. Tim Elliott plays his part 8,000 miles away.
As geochemists, we tend to come in after the thing's cooled down and then knock bits off.
Predicting eruptions is every volcanologist's aim, but it makes predicting the weather look easy. Lava samples tell us that the Earth's composition is complex, and it changes whenever a large earthquake or eruption occurs. For Tim Elliott, who struggles to keep tabs on this shifting underground world, every sample is a rich source of information. For what will eventually be a highly sophisticated piece of analysis, Tim starts by crushing the lava in a machine Jules Verne might well have designed himself. The first thing is to break the lava into pieces. Then, it must be crushed into a fine powder. The next step must be done with great care. The hydrofluoric acid Tim uses to dissolve the powder is equally good at dissolving skin and bone. It eats all the rocky parts away, leaving just the base elements. Those are the parts Tim's interested in. The lava sample is heated and the acid evaporated off overnight.
Once we've got a pure separate of the element that we want, we then take that to the mass spectrometer to analyze its isotope ratio.
Wherever they come from, any two samples of a chemical element will be chemically identical. But we now know that they can differ physically. A mass spectrometer can tell them apart and tell Tim just where in the Earth a sample came from. This one came from very deep indeed.
So that maybe gives us a clue that these things come all the way from the core mantle boundary. But in terms of the ultimate depth of these things, to some extent, I hate to admit it, we rely on the seismologists.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Seismologists can see inside the Earth without going there. Their explosions create shock waves of sound. When the waves hit rock, they bounce back to sensors on the surface. Since different rocks reflect waves at different speeds, seismology lets us map the Earth's subsurface landscapes. Can today's technology take us to the center of the Earth? If so, what would we find there? Seismology lets us see with sound. And there's more to it than creating big bangs, as MIT's Rob van der Hilst explains.
Seismology is pretty much the only way to get fairly direct probes of the Earth's interior. And there's a lot of development in the seismic theory and observational seismology itself to really give much more refined images.
Seismology is similar to an ultrasound scan that can show an unborn baby in its mother's womb. An image can be created because sound travels through different parts of our body at different speeds. Unlike this scanner, which generates its own sound, seismology can make use of natural sounds that occur every minute or two. The sound of earthquakes. Thankfully, we don't notice most of them, but there are actually 1 million a year. And they're shaking up our ideas about what's going on thousands of miles beneath our feet. Earthquakes are appallingly destructive to human life, but to scientists, they have their uses. The seismic waves are like sonar. By listening as they pass through the Earth, a picture can be built up of a place no one can ever see. First, the waves race through the crust, the skin on the planet's surface. In some places, only 4 miles separates us from the intolerable heat of the magma in the interior of the Earth. The temperature is nearly 3,000 degrees, so intense that the rocks are partially melted. 3,000 miles down in the core itself, the temperature reaches an unimaginable 7,000 degrees. It is the ultimate nuclear reactor, the engine driving the planet.
What we can really image very well is the material that goes down, and in some cases we can see down to the core mantle boundary. And all that information tells us a little bit about, how density is concentrated in the center of the Earth and how density changes with increasing depth.
Seismologists image rocks. Petrologists make them, mimicking the heat and pressure of the deep Earth.
Now we know where they come from, we know how deep they come from, because the minerals contain elements like calcium and aluminium, and the distribution of these elements between the different minerals depends on pressure. So by simulating the pressure, taking a sample like this and subjecting it to high pressure, and seeing how the compositions of the minerals change as we change the pressure, we can go back and work out what depth this particular sample came from.
The anvil on which Bernie forges his man-made minerals is made of tungsten carbide, a material so hard we use it to make drills. He puts a tiny sample of rock in a ceramic tube, a miniature furnace, and then walls it up. The bricks are specially shaped to focus the force he'll apply to them. This way, he aims to reproduce the massive pressures to be found in the Earth.
Over a period of about 4 or 5 hours, we raised the force to around 500 tons, and we then apply a current to the furnace, which is in the middle of that lot, in order to raise the temperature to 1,700 degrees C.
The petrologist awaits the outcome as anxiously as a pizza chef. If the heat and pressure are right, the elements will fuse together into an exact copy of the mineral he's studying. This tells him where it came from. In this case, 440 miles down, where the pressure is 250,000 times higher than at the surface. The advances in science since Verne's time have been breathtaking. And we're still discovering how the Earth was made and how it continues to change. We've come a long way, not in distance, but in knowledge. We've ventured 200,000 miles into space, but as yet, we've only been 7 miles into our own planet. With all the knowledge and technology we have today, surely we can tunnel to the center of the Earth. If we could tunnel to the core, the rewards would be huge. We could shut down our power stations. The energy we tap into would never run out. It would be free and cause no emissions. We could dispose of dangerous waste in the world's hottest incinerator. Huge quantities of minerals are there, just waiting to be brought to the surface. Maybe we could build a high-speed transportation system through the Earth, a global subway. But it's not that easy. This tunnel, linking England and France, took 5 years to construct, and it's only 30 miles long. It's 4,000 miles to the center of the Earth. And would we actually want to go there? It's an adventure that Dan Lathrop would welcome.
That was an interesting idea for an adventure. I guess I'm ready to go if it becomes possible.
Meet the team that's designing the first vehicle capable of penetrating to the center of the Earth. Today's tunneling machines have brains as well as brawn. They drill and support the tunnel as they go, and never stop. But what chance has even a smart monster like this of getting to the center of the Earth? Brian Clark has built tunnels all over the world.
If we're tunneling to the center of the Earth, there are different combinations of material, but generally we would start in soft ground tunneling. We would move through into rock, and as we go to extreme depth, the rock would change in character due to the temperature effects. We almost certainly would need to use an arm with a cutter head, tungsten carbide teeth on it to grind and smash the rock.
Today's most advanced mechanical moles can dig 2 feet every hour. At that rate, tunneling 24 hours a day, it would take 1,000 years to reach the center. We'd have to make them work faster, much faster.
And if you think of the tunneling machine as a very large beer can, and it's travelling end on end down through the Earth with cutters up front, the closed face, it means that the cutters cutting away at the soft ground are separated by a wall from the men on the inside, and all of the spoil, all of the earth that's being cut, is carried to the surface in pipes.
The amount of rock and spoil coming out of the tunnel is almost unimaginable. We'd need to extract 4 giant truckloads of earth per hour, 100 per day, 36 million truckloads in all. And that's if we tunneled straight down, not on a grade. We'd have to design a new type of vehicle to transport us through the tunnel. Maybe a capsule able to withstand the extremes found deep inside the Earth.
The deeper we go, for every kilometre in depth, we're picking up a 30° centigrade temperature rise, and that is causing us problems. The rock is getting softer, it's getting ductile as a result of the higher temperatures. We're having to resist those temperatures so that people can work within the tunnelling machine, or we would need to produce a remote machine. I think we're now stretching credibility.
But it's not only temperature that will be a problem. There's also massive pressure down there.
Yeah, I would say it would be incredibly difficult. I think in comparison, the environment as you go deeper into the center of the Earth is much more harsh than what you would find, for the most part, for space travel. With the temperatures and the pressures you'd find.
It's actually a much more hostile environment than going in space or down in the ocean. And in particular, the high pressures are such that we wouldn't know how to make a vessel that you could go inside and not get crushed down, really past a few miles. The pressures would start to get too high for any sort of normal technology.
We have ignition sequence start.
We already know a thing or two about building complex vehicles. Could we spin off space technology to help get us to the center of the Earth?
Clearly, one of the biggest issues you're going to have with a trip like that is going to be the extreme temperatures and pressures. Some of the best materials that we have currently for dealing with temperatures like that would be the ceramic tiles in the shuttle, or some kind of carbon or any type of carbon-based material.
But here's the hitch. While man-made materials like ceramics and carbons withstand heat, they lack strength. Metal is strong, but most steel melts at around 2,500 degrees. The temperature at the Earth's core is probably 14,000. We need new materials to build our capsule, or to shield it.
Sometimes, if time is on your side and you're not going to be exposed to the temperature for very long, simply having a material with enough heat capacity to absorb the heat that's flowing into the system without melting would be sufficient. The best bet that I know of as far as temperature is diamond. And even diamond, I think, has a melting temperature of 3,200 Kelvin. So from a material standpoint, I don't know of any materials on their own that would be able to withstand those temperatures.
As well as being the ultimate adornment, diamond is the hardest substance known. We can manufacture diamonds, but could we make one big enough from which to build a capsule?
Well, the diamond certainly would be the strongest material and would allow you to have the highest pressures. It's not entirely clear you, of course, can fabricate an entire vessel out of diamond. That certainly would be an interesting thing and useful in itself if someone could work it out.
For the capsule to survive, it would have to be continuously cooled.
The most difficult thing to overcome is being able to get the heat away from the craft. So the only way to be able to stay in temperatures like that or to be able to extract the heat. Maybe someday with some type of carbon nanotube technology, you could have a very long tether that would follow the craft down to the center, and you could pump some kind of coolant that would go down for thousands of kilometers or however far it had to go and draw the heat back that way. But without some type of active cooling, I can't see how you would do it.
The biggest problem is the length of time the capsule would be exposed to the extreme heat.
It'd be like trying to build a ship to go in and skirt the sun, it would be that, that sort of nasty high temperatures.
Since the center of the Earth is as hot as the surface of the sun, we couldn't begin to survive there. Space has enormous challenges, but most of it isn't hot. It's a vacuum, so there's no air. But you can take or make your own. And in a vacuum, spacecraft and spacesuits don't have to resist colossal pressure. Exploring space is no picnic, but it's a cakewalk compared to exploring the inner Earth. Every 200 years, this city is devastated by earthquakes. The next one is overdue. Can our Earth capsule save the 12 million people who live here? A tunneling machine using conventional technology would be destroyed by heat and pressure long before it reached the Earth's center. Only 20 miles into its 4,000-mile journey, it would melt. But if one day we could conquer these technical problems, there may be a way we could send a capsule deep into the planet. We'd have to harness the most powerful force on Earth, continental drift. The theory of continental drift, also called plate tectonics, was finally accepted by science in the 1960s, a century after Jules Verne's day. It said that the land masses we're familiar with started out as one supercontinent. This sat on plates that migrated across the globe. But the plates haven't stopped. In another 20 million years, our world will look very different. This is the San Andreas Fault. These two plates are sliding past each other. At the same speed your fingernails grow. Most of the time, these plates slide smoothly, but occasionally they get stuck. And this causes earthquakes. Plates don't always slide past each other. In some places, one plate is forced beneath the other. That's what's happening underneath Japan. It looks serene, but beneath the surface, it's a different story. The Pacific Plate and Asia are colliding head-on. Below the picturesque landscape, the Pacific Plate is being driven under Asia, a process called subduction. It makes Japan a hotspot, not just for volcanoes, but for earthquakes as well. Japan's volcanoes look genteel, but don't believe it. It's feared they'll destroy the islands they once created. If we could take our capsule deep below Japan, we'd find that the volcanoes aren't like the ones we saw in Hawaii. At Kilauea, the heat and pressure of the deep earth blast out streams and fountains of molten lava. Under Japan, there's a different driving force beneath volcanoes: subduction. As subduction buckles and breaks the Earth's crust, seawater flows in. Hot rock and cold water are an explosive mixture. Subduction triggers earthquakes too. Tetsuro Orabe is a professor at the University of Tokyo. 8 years ago, a quake killed 6,000 people, including his mother. He now works on earthquake prediction.
Japanese island arc locates on the western rim of the Eurasian continent, where the plate of Pacific Ocean floor goes down beneath the island arc. So that kind of active setting makes all those natural disasters like a volcanic eruption and earthquake. In 1995, there was a Kobe earthquake which killed about 6,000 people, but it was not predicted, and all the seismological method failed to predict the earthquake.
To predict earthquakes better, we have to know more about their causes. A capsule designed to travel to the center of the Earth could help. If we weren't in a hurry, we could bury it in the Pacific Plate and wait for a few million years. It would end up under Japan, courtesy of continental drift and subduction. The rock we parked the capsule in is solid, but also moving.
And this is what the mantle does. It flows very, very slowly at about a centimeter or so a year. But like glass, if you hit it with a hammer, it breaks.
And that's what causes an earthquake. 150 miles down, one plate tries to move against another. Incredible pressure builds until one slab breaks and slips. Because of its unstable foundations, Japan has one of the most comprehensive networks of earthquake sensors in the world. 1,700 underground sensors listen out for a hint of movement in the crust and mantle. The data is beamed back to a national monitoring center that records every tiny moan and groan. Every quake, however small, is mapped in 3 dimensions. The quest is to find a pattern that will predict future quakes, because Japan is due another big one. It's expected here, Tokyo. Tokyo has a population of over 12 million. Every 200 years, this area is hit by a huge earthquake. The city is built over a busy intersection where 4 of the Earth's plates meet. The subterranean collisions never stop. That's why Japan's so prone to earthquakes, and why it's so hard to see them coming. It's a high-stakes game. Millions could be hurt or killed. To get better data, they will have to drill down into the colliding plates, more than 6 miles.
JADGE stands for Japanese Ultra Deep Drilling and Geoscientific Experiment. That is to drill about 10-kilometer hole down to the subduction zone.
They've chosen a site, but what about the technology?
The target area of the JUDGE project is very active, and probably the temperature could be more than 300 degrees at the depths of 10 kilometers. And then 300 degrees makes every operation of the drilling very difficult.
And that's the same for our capsule. We'd need more technology for it to survive the intense temperature and pressure. What will the capsule find at the center of the Earth? A mammoth nuclear reactor? On its way to the center of the Earth, our capsule will have to navigate a sea of molten iron. Surging around the inner core, this generates magnetic energy. Just 1% of it escapes from Earth, but that's enough to form a protective shield 37,000 miles out into space. But how is so much energy produced? As Jeremy Bloxham admits, we're still struggling to find out.
Really, the burning question which we all wish to address through our investigations of the Earth's magnetic field is, how is the field generated? What is the mechanism that gives rise to a field which has persisted for at least 2 billion years?
One geophysicist has a radical suggestion. Marvin Herndon speculates that at the center of the Earth, we may find a natural nuclear reactor.
One of the problems that has existed in science is figuring out what is the energy source that drives the Earth's magnetic field.
He doubts that it's just a ball of iron that's been cooling for 4.5 billion years. There's simply so much power. Enough to maintain the magnetic shield, move continents, and make volcanoes and earthquakes. Herndon suspects there's something much more powerful down there.
One of the implications that I suggested early on was the possibility that the changes that we observe in the geomagnetic field may have their origins in changes in the output power of the nuclear reactor.
Could this explain the drastic changes our planet has gone through? Like the extinction of the dinosaurs? Could the melting of the ice caps have been caused by a surge of heat from a nuclear core? Because unlike an iron core, a nuclear one can fluctuate.
A nuclear reactor can shut itself down and start itself up again. Its output can vary, or it can remain very constant.
Herndon's ideas are controversial. Few agree with his theory, and the debate continues. But one thing isn't disputed. The magnetic field is changing, and measurements show it's been doing so for some time.
Based on the results in our current systems that are sort of basketball size, then we have this plan for a much larger system that would be 10-foot in diameter sphere filled with liquid sodium, so about 15 tons of the metal. But it would be driven the same way as the existing experiments, but then at parameters that are much closer to the parameters thought to exist in the interior of the Earth.
The capsule we built to journey to the center of the Earth is under its own power after hitching a ride in the rock. Now, sensors show the going is about to get tough. 1,500 miles down, the capsule nears the boundary between the mantle and the outer core. The huge temperature here melts away the remains of the tectonic plate surrounding the capsule. Now, the capsule must be released from its protection and power itself. The capsule drives forward through the liquid outer core. Now, it must cut its way into the solid inner core. It's solid because there's massive pressure here, 4 million times greater than at the surface. And 1 billion amps of electricity surges between the cores. This, at last, is our journey's end, the center of the Earth. The only place on our planet with no gravity. Jules Verne's influence on the world has been immense. He propelled generations of young readers toward careers in science, engineering, and exploration. He inspired the inventors of the helicopter, the submarine, and the radio. There's little doubt that his novels influenced the minds that have changed our world. Little did anyone know, when Jules Verne died at the dawn of the 20th century, that he would have such an effect on the future. His life is summed up in the inscription on his tomb: "Onward to immortality and eternal youth." If Jules Verne was right, maybe one day we will be able to journey to the center of the Earth.